Previously in Chapter 3, we've talked about measures of central tendency and measures of variation. So we did mean, median, mode, mid-range, things like that, standard deviation, variance, range, things of that nature. Now we're going to talk about measures of position. How can we compare things position-wise in relation to their other data? We're going to start off, we already have our vocabulary taken care of. When you're talking apples versus oranges, can we compare apples and oranges? Well, the answer, truthfully, is that yes, we can compare apples and oranges. It just depends on how you set it up. So, we talk about using standardized data or standard scores, or z-scores is what we use. A lot of you learned about z-scores in Algebra 2, but we're just going to go over it real quick. So what happens is we equate two sets of data that are not in the same area on the number line, or maybe they are, but they don't have all the same mean and standard deviation, and we set them up with a relative standard so that we can compare two different types of data. And you'll see what we mean as we go along. Our Z formula, the value is your actual data value. Remember, mean is X bar for a sample or mu for a population. Standard deviation is S for a sample or sigma for a population. So you have your sample formula and your population formula. A couple of things about that. First of all, both formulas say the same thing. They just, one of them uses the information from a sample and the other from a population. When you use your calculator and one variable statistics, a lot of times when you look at that, you got to remember, do I use S or sigma? It gives you X bar, so you know which mean you're using if you're on that data set. But if I'm doing my standard deviation, do I use S or sigma? Also, for the purpose of this section, all of our data is taken from samples. For this section, use samples. Okay? All right. So down here, what does the z-score actually represent? The number of standard deviations that your data value falls above or below the mean. So when we're looking at this, let's talk test scores real quick. We'll look at our example. This is talking about how many points somebody got on a test. What was their score on the test? So the student scored an 85. The mean score was 76. The standard deviation was 4. So all of these would be points on the test, right? So our mean is 76 points and our standard deviation is 4 points. When you convert to a z-score, the z-score does not represent any points. It represents how many standard deviations from the mean. Okay, so let's see if we can understand this. In this first example, we're talking about a student who took an English test and a French test. Okay, on the English test, the student scored 85 on an English test. The mean score was a 76. The standard deviation was 4. She also scored a 42 on her French test, which sounds horrible when you start talking. But the class mean was 36 and the standard deviation was 3. And they want you to compare the relative positions. Well, if I did this with the actual data that were given, the French test with a 36 as its mean, and standard deviation is how many places you move over at a time. So 36 plus 3 plus 3 plus 3. And then below the mean, you would minus 3. So this would be 33, 30, and 27. There's the distribution of my French test scores according to this. Can they go further than that? Yes, but this is where we generally look. All right, then we talk about our English test. I'm going to break my axis right here because these scores jump a long way on the number line and it doesn't all fit together exactly right. So 76 here, and the standard deviation was 4. So whereas this was only 3 over here, we're going out 4. Every time we move, we count by 4s. So 76, 80, 84, 88. Here we have 72, 68, and 64. Okay? So you see that my data for the English test is a little bit spread out further because it has a bigger standard deviation. Not by much, but some. So the actual data was an 85 on the English test. So that puts the X value about right here. It was a 42 on the French test, which puts it exactly here. Okay? But when I try to compare these, a lot of people get confused because obviously 42 is way lower on the number line than 84 is. Plus, you automatically see 42 and think, oh my gosh, what a horrible test grade. But if you're just comparing it in this set of data, it's really not bad at all. So what we did was we found our z-score for the French test, because that's the one that was on this end of the number line. The actual score was a 42, the mean X bar was a 36, and the standard deviation was 3. So z equals 42 minus 36 divided by 3, which is 2. Sorry, my brain blanked for a minute. On my French test, or sorry, my English test, the actual data was an 85. The X bar, the mean, was 76, and S, the standard deviation, was 4. So Z equals 85 minus 76 over 4, which gave me 2.25. By the way, Z-scores are always rounded to 2 decimal places. So what does this mean to me? This means that the French score was exactly 2 standard deviations above the class average. And then the English score was 2.25 or 2 1/4 standard deviations above the class average. So instead of having this number line with all these crazy numbers everywhere, I can do one number line. When I'm dealing with z-scores, my mean is 0 and my standard deviation is 1 because we're counting by one z everywhere. So we could say that my French score was right here and that my English score was just a little beyond there. Okay? So it's just talking about the position. It's not talking about necessarily better or worse, but the position. All right, one more. Let's do this one. I recommend highly that you pause and figure this one out, and then we talk about it. I'm going to go ahead and set this up. Men versus women. The fight for the ages, right? But in this one, we're saying that the mean age at which men get married in a recent study is said to be 26.4 years. Well, I want X bar, S. I work with patterns, so I keep in the same order. My X bar for men is 26.4 with a standard deviation of 2 years. The mean age at which women marry is 23.5, X bar, S. So this is 23.5 with a standard deviation of 2.3 years. This is find the relative positions, which are z-scores, for a man who marries at age 24, that's the actual data, and a woman who marries at age 22. Well, a lot of people are going to say, well, obviously the woman is younger than the man. Yes, she is. That is correct. However, when we talk about relative to the data, we have to do our z-score. Z-min is 24 minus 26.4 divided by 2, which gave me negative 1.2. And the z-score for the women was 22 minus 23.5 divided by 2.3. I'm filling in the formula. And my z-score for women was negative 0.65. So what does that mean? It means that the man who got married was 1.2 standard deviations, 1.2 standard deviations below the average age of men getting married. The woman was less than 1, so 0.65 standard deviations less than the mean age or the average age of women getting married. If we looked at a number line for this one, again, 0, 1, 2, 3. We usually just count out by threes. There are going to be z-scores that are higher and lower than negative 3 and 3, but for our visual, this is what we usually look at. So we know that the z-score for women fell somewhere about right here. and the z-score for men fell somewhere about right here. All that means is that relatively, the man was younger compared to his male counterparts than the woman was compared to her female counterparts. Okay? All right, so that's all for z-score. Oh, no, we already talked about it. When I'm using z-score, let's remember this. We use x bar or mu equals 0 and standard deviation s or sigma equals 1. When you're using z-score, that's what we use. All right, that's it for z-score. We'll be back with percentile.